Hello. Good morning, my dear faculty members and participants. This is Dr. K.C. Kulayappa, HOD of Electronics and Communication Engineering, Gates Institute of Technology, convener of the 5-day faculty development program on research trends in image processing. Welcome you all for the 4th day session. Hope yesterday everyone had knowledgeable session on similarity learning in content-based texture image retrieval and similarity learning in content-based image retrieval using multiple classifiers by Dr. S. Mukhopadhyay garu. After this insightful session, today we are having an excited and informative session on computer vision applications in remotely sensed images. Morphological operations and applications in image processing. Now I take this opportunity to introduce today's speaker, Dr. Jibanananda Rai, sir. He received Masters in Mathematics and PhD in Image Processing from IIT Kharagpur in 1996. Currently, he is a Director, Texellation Software Private Limited, providing consulting services on artificial intelligence and machine learning applications to manufacturing industries, natural resource management organizations, and government R&D institutions. Dr. J.A. Rai sir has 30 years of experience in ISRO and industrial R&D. Dr. J.A. Rai worked as a scientist in ISRO Department of Space for 15 years. At the Department of Space, his primary role was to carry out research and development in the field of digital remote sensing and geographical information system. He has successfully executed projects in automobiles, electronics, satellite imaging, and computer vision. To his credits, he got 3 patents in USA and UK on digital video. He has guided 3 PhDs and more than 100 MTech students. He has given guest lectures in academic institutions on data science, digital image processing, and computer science applications. Now I welcome Dr. J.A. Rai garu to take over this session and enlighten us with his experience.
Okay, thank you, Dr. Kulayappa. Today, in the first session, I'll be talking about the morphology. The mathematical morphology, it started about in 1960s, but it has become recently very popular. Let me share the screen. Is the slides are visible?
Yes, sir. It's clearly visible, sir.
Okay. So use of mathematical morphology to image analysis. I'm speaking on that. So it was developed by Professor G. Matheron and Jean Serra, the School of Mines, Paris. Incidentally, initially it was developed for petrography and mineralogy to analyze, the rock samples what they bring and polish it, and on that they do the grain analysis kind of thing and study the geometrical structures. So they started developing a technology for petrology and mineralogy. And finally, by 80s, it was a full-fledged approach to image analysis called as mathematical morphology. What is morphology? But in morphology, morph means shape or form. So it is the study of forms, shape, or structures. Unlike in normal image processing, what we developed, we are used to see images as a two-dimensional structure. It's a rectangular array of points or pixels. It could be binary, it could be gray level, it could be colored, it could be hyperspectral, different kind of images, but essentially they're a two-dimensional array. And in some cases, there may be multiple images which are used for extraction of 3D. But in morphology, the images are considered as geometrical structures. So analysis is done on the geometrical structure of the image. The basic idea comes from the geometrical structures which are operated by another geometrical structure. Usually it is much smaller one, which is known as structuring element. To extract information about the shape, structure, geometrical features, topological features, etc. And not the kind of analysis we're used to see like convolution, or in the frequency domain, the signal analysis. Here, the whole image, it is operated. It was developed initially for binary images, and it was later extended for gray level images. Currently, it is being used to all kind of images like color, hyperspectral, and all. But what is the advantage of using this? Now, if you think about the binary images those days, now it is during 1990s when the computers were not what we used to see, the high-speed computers were not there. It was still serial computers, and there were some dedicated parallel processors. Now, with binary, I mean, it used to take a lot of time. If you think about the kind of computers were there, I can tell you, we were working with systems which had a memory of 64 kilobytes only. So these kind of systems were there. So that time we had the hardware implementation also for imaging. Now, since it is binary image and the operations are done with another binary image. So binary image means bits 0 and 1. Now in a computer word, which is usually 16-bit or 32-bit, you can pack the whole data, the binary image. Suppose 32 points pixels you can pack in one word. And as you know, in computers, working with words is faster than using each pixel, because each pixel, if it is a binary value, the operation time will be same if you use word. So by packing multiple points as integers or the equivalent word size of a computer, in a serial computer, if you run it, it used to be very fast. And since the morphological operations are usually, it is shift. I mean, shifting the image on left, right, top, bottom, or in the corner. And operations are binary operations like AND, OR, XOR, set difference, and all. So it was easy to do the parallel implementation because the whole image you could shift on left side or right side and carry out ANDing or operations. This way you can implement the morphology. Now, how binary images are represented as 1 we say as foreground and 0 as a background. In morphology, we have two basic operations, which is known as erosion and dilation. With these two operations, simple operations, you can implement many different algorithms here, almost all kind of image processing algorithms, which is called erosion and dilation. And there is one transform called heat or mist transform. Now, what are the use of morphology mostly? As you see, noise filtering, shape simplification, enhancement, skeletonizing, thinning, thickening, convex object. These are all image processing problems, usually in the computational geometry, application of computational geometry in image processing. Then segmenting objects from the background or finding the quantitative description like area, perimeter, projections, etc. Now let's see the simple problems. You see here, there are two objects. This is an object, a rectangular object. This is another elliptical object. And these points, it may scatter everywhere. These are known as noise. It is very usual to see images with graininess or grains, you can say. These are very simple, clean image here, just for the illustration I'm using. But normally, if you take up any digital image or if you scan an image, you will find there are a lot of dots here and there. If you have black and white dots, we call it salt and pepper noise, or we say there are speckles here and there. So in image processing, we have despeckling, and there are different kind of techniques. Usually you use a average filter kind of thing in convolution, or median filtering kind of thing. Each has got its advantage and disadvantage. But in morphology, since the approach has started, it is a different kind of approach to dealing. So it starts with the beginning. I can tell you that how it works. Now, this is one of the problems, how to remove these noises. This is a basic problem in image processing. Most of the images, what we use, even when we take with the mobile camera or we do the scanning, we find this is the basic problem. Though we have now the implementation in the software itself, like in a mobile camera, you have despeckling and all. It's for the tube, but you should have the knowledge of this so that, I mean, the inbuilt softwares do not work all the time. It may not work with the way you want to be. This is another problem. Often you'll find the two objects in an image are touching by a thin line or something like that, or they may be touching, both may be touching together. We know that there should be a gap here. There should not be any connection. It's two different connected components, because unless you do this cleaning, you cannot do a lot of operations like counting. Suppose your problem is to count objects, or suppose your problem is to find out the rectangular area in an industrial inspection system. You need to separate out the objects. How to separate these two components? This kind of problems usually morphology addresses. Is another problem. There are two objects, and how to label these two components separately. Like this should be labeled as 1, this should be labeled as 2. But what we have got is series of ones. The background is 0, but all ones here, all ones here. How to compare these two shapes? They are almost similar. We have different kind of, shape numbers. There are different kind of shape measures which are used. We have been developed to compare these two shapes, whether are they similar or are they having different area. So morphology helps us to do this. We come to the mathematical basis. Initially, the morphological operations were defined on hexagonal grids. Now, why hexagonal grid? Because the hexagonal grid, the property you can see that from a center, if you take the different pixels, nearby neighboring pixels, they are all equidistant. So mathematically, when you write something, so you should have that all pixels are at the same position, I mean, at the same distance. Otherwise, the theory, the background, the theory doesn't work. So for theoretical development, it was assumed hexagonal grid. But in practical purposes, we cannot use any hexagonal grid. Number one, we are used to seeing rectangular grid. And it is easier to implement in a computer if you have a rectangular grid. These are rectangular grid, if you see, but as you can see, these are if the horizontal and vertical distances are at 1 unit, the corners are at √2 units. So they are not equidistant. Now, if we connect a path, if we want to find out what is the length of the path, then you have to write this one and this is √2 like this. It's not as simple. And when you do processing also there at a different distance than the horizontal. But for simplicity, we use rectangular grid. And also our discussion will be on rectangular grid only. Now, mathematical morphology it has been developed with very high level of mathematics. The basic is set theory, but it uses integral geometry, lattice theory, Minkowski operations, algebraic systems, topological space, and different kinds of even normal topology, geometry. We'll not go to the mathematical basis, but there is a strong mathematical background to the development of morphology. That's why we talk so much about the clarity on the mathematical assumptions, like using an hexagonal grid, because unless you have a rectangular grid is an approximation to us. It makes our life easier. We use it, but it's not, the rectangular grid is not what it should be, because in rectangular grid, you can go only horizontally or vertically. You should not go in the corner wise, because if you go to the corner wise, like 45 degree, 135 degree and all, if you go, then actually the distances are not same. So you cannot say a pixel which is nearby horizontally or vertically will have a similar spectral characteristics like in the corners. So the strong mathematics is there, which we are most of the things we'll omit here. Only the basic understanding. Let's see, what is a binary image? A binary image, if you go to the set theory, what happens? A binary image is a two-dimensional point set. You can also consider it's a subset of the Euclidean space, two-dimensional Euclidean space, or normal coordinate geometry, the way we see that there is a x direction, there is a y direction, and there is an equal interval. You have got a point, which is known as the resolution. So a binary image is a collection of points. Now, when I say it's a 2D point set, I'm talking about there are two things. One is called the foreground, one is called the background. The foreground means where you have got the pixel values as 1, or in computer when we implement, we write 255 and the background as 0, or vice versa also it is used. But the foreground, you've got some points which are known as object points, and the background, which is basically the complement of the object point, so which is 0. So what are morphological operations? The basics of morphological operation is an operation on the point set X by another point set B. And the B is called structuring element, which is very important because your choice of structuring element gives the kind of processing you want. In a structuring element is again, it could be a rectangular, it could be horizontal, it could be vertical, it could be diagonal. But for ease of implementation, you can say that wherever there is not 1, we can write as 0. The position where you have got 0 are called, I mean, not background, but which we call as don't care locations. Only where 1 is there, we're interested to work, only where 1 is there. And there is always an origin. Usually you can take a 3x3, 4x4, 5x5, depending on the kind of application you need, the structuring element. What happens? We move the structuring element over the image such that at each point of the object X, that means where you have got 1, we overlap our structuring element coinciding with the origin. This is something like your convolution, but you are, I mean, if you see differently, it's not exactly a convolution. And then we carry out some set operations like and or in a gray level image, we do min max kind of thing. But this B is moved over X with each point coinciding with the origin of B. I mean, the whole image should be covered. Let's see some typical structuring elements. What we have? See, it is 3x3 and some positions are blank, which we call as don't care. You can see here we have got in the horizontal vertical position. Here you have got is a isometric or isotropic where every point is there in a 3x3 neighborhood. Now the difference here and here you can see this is our origin, this is also our origin, but here this is our don't care location. Because we won't be considering these points, we'll be considering only these 4. But here we'll be considering these 5. We have got similar operations in our normal image processing in a convolution, or when we do the median filtering, sometimes we consider the same point, or sometimes we exclude the central point, the point you are going to replace. So here it is excluded, here it is included. Now it is not necessary that your structuring element, the origin will be at the center. As you can see, here is the our origin. And not necessarily it will be symmetric, as you can see here, because it depends the kind of operations you require, whether you want to do the thinning kind of operation or erosion, or you want to find out the edges, or you want to do some segmentation or skeletonization. Depending on that, you have to use the kind of structuring element and the center. Here you can see it is a 3x1 structuring element, and you've got your origin here. So it is not necessary that you should have a 3x3 or 5x5 kind of structuring element. You can have 1x3, 3x1 also, and it may not be horizontal or vertical, it may be diagonal too. Now we go to the duality principle, as in the set theory we have, which is known as that for every operation there is an equivalent operation. So here, if you do the morphological operations on the set, so there always exists a dual transformation, such that if you operate the operation on the foreground, and if you operate on the background, now the background, that means what? In the background, when you operate, we will convert them as 1. We consider the zeros as 1, and then we do our usual processing. So there is always another transform. If you work on the background, and take the complement of it, we'll get the same thing. So this is known as the mathematical duality, that for every operation, we have got another operation done on the complement. And if you take the complement, you get the same thing. So we consider E is the 2D Euclidean space, and translation of set X by vector H is defined as X plus H, X belonging to X. I'm going out of it and share a new one. Just 1 minute. Okay, I've taken out this from a book. This is the first lecture I'm giving online, and it is difficult not to use a board with a chalk and write it. Now let's see what is erosion. What is erosion? As we know in English language also, like on the river bank, erosion means it is when the water recedes, the soil recedes and the water, so that is called erosion. So in binary images, erosion means it is the shrinking. Now, how much shrinking is required, which direction is required, that gives the structuring element will define what is shrinking, how much you want to shrink by erosion. So as you see, if you use this is your structuring element, and if you use on this image, the erosion means if you erode with this structuring element, only the horizontal and vertical pixels on the boundary will be removed by the operation, as can be seen here. Now, instead of that, if we had used, though this image is a very nice image, now that's why we've used this kind of structuring element where you have got only vertical and horizontal points as the structuring element. Instead, if the image is having some curves, then we need to use a 3x3, even a 3x3 structuring element with the diagonal elements too. Then we'll get the boundary pixels will be removed by erosion. So how erosion is defined mathematically? The erosion means if you place your structuring element on the image, then the whole image, the whole structuring element should be contained in the image. Then only that pixel we say it is we satisfied the erosion. So if you use such a structural element of the image, then finally we'll get a thin line. And here, Here, if you move, actually the idea is if you move over this, see inside when I take, it is contained. But if you take outside, just if your center is here, then this point does not satisfy the property that the structuring element is contained or is a subset of the set. So that only the boundary pixels, these will be removed, as you can see here. And if you use such structuring element, then we will get only a horizontal line. So it depends on what kind of applications you need. Now remember what we have got in erosion. It's a very important property, will come later. Now erosion removes unwanted noises too, like some kind of structures, some kind of noises we can remove. As I've seen my initial slides, that you can remove salt and pepper kind of noise. That means if you have got dots here and there, you can remove it by suitably choosing your structuring element. Now you see the effect of erosion with a varying structuring element, where everything is a 3x3 structuring element or 4x4 or whatever it is. It's isotropic. I mean, everywhere all points are there, 3x3 or 4x4. Now these are original image, and probably these are all 11. If you use 11x11 structuring element, see what has been removed. The thick lines have become thin, and these lines have been removed. So this is the effect of using a 11x11. Now if we further increase it, then some more lines are, these lines are also removed. And if you further increase it, then you get only the box here. Now, as you can see here with this example, that depending on what you want to remove, you should choose your structuring element and the size and the shape of the structuring element. A dilation, you can say, is just the reverse of what erosion does. What is erosion? Erosion means it removes pixels, but dilation, it adds to the foreground. That means what? Here in the erosion, we say that if you move the structuring element over the image, then the structuring element should be fully contained, or it should be a subset of the original set of the object set. Then only we say erosion. But for dilation, it is known, we can say, if it touches or if it heats, it is known as heating. So as you can see, your structuring element, actually what we do with the structuring element, you can think about you can think like a digital probe. So you're probing the digital image with a probe to find out certain geometrical features. So now if we move, dilation means if you move this one, this structuring element over the image, if it touches, then those points will be considered as the new point of the dilated set. That means it is some kind of expanding. You're getting it expanded. Erosion, it is shrinking, here it is expanding. So when you move on this, you see, by this size, actually it is by half size, it will increase. Why it is half size? Because it has to come to the center. You have to overlap. You have to overlap on the center. You have to place it at the center should be placed on the image. Now inside anywhere you put it, those points are anyway included. But in the boundary pixels, you will see that one additional one will come. Like here, half a distance if you take out, then also it will touch. So if it hits or touches, then it will be part of the dilated set. So this is called the dilation. You see, the original image has been expanded. You have taken the structuring element as a square one. And if you take something like this, elongated one, then the effect of this, it has gone only on the vertical direction, it has extended. You can take any different kind of structuring element depending on the kind of processing you need. These are some of the applications. I'll zoom it so that you can see the effect. Have you seen the effect? What has happened? This is the original image. Because it is scanned, after scanning, in some places, even if you do the scanning, a old book, you will see that in some places it's not clear. So if we use a dilation kind of thing, then it will fill the gaps. So dilation is also used to fill the gaps. We'll come to a better approach, much more sophisticated one, but you see the effect. But what happens if you use a dilation? It is sort of you are doing a low pass filtering. So your sharp objects, sharp boundaries will become blurred. Here, as you can see, the input and this is the output. And only 4 connected structuring elements have been used. This is a new concept, though not new concept. It is your basic is always erosion and dilation. But by combining erosion and dilation, you can generate other operators. In morphology, there are standard operators called opening and closing. So in opening, what it does, in opening, it will remove, or it will, as I've given in the initially, that how to separate out 2 objects which are touching. So you can first erode it and dilate it. So this is known as opening. But in the process, it will remove the sharp corners. So this is called the let's see. Oh, it removes the sharp corners if you do only erosion. If you do erosion, suppose with the ball, it will remove the sharp corners. And here, if you do that first dilate and then erode, then you see it is given as a ball. If the ball moves, then it feels the whole thing again. So this is called rolling a ball on the set A or on an object. You can see some of the examples here. What happens if you use?
Sir.
Hello? Hello?
Sir, continue, sir. Continue.
Okay.
Sir.
Okay. You can see the effect of opening and closing and what it happens on the, what effect it has on the topology of the image. Here, if you go on dilating and eroding, then it will finally touch here. Or The opposite is this here. Where these are used. This is an example. Suppose as you can see, it is a thumbprint. Now, when you take the thumbprint, even when you use, nowadays, we are using a thumbprint scanner in many places. So the scanner will have dust, or everybody is using is there will be dust. And then when we take, you will get some small. Is it visible, Professor?
Sir, it's clearly visible, sir.
Yes,
Okay.
clear.
Okay. So as you can see, there are dots will come when you do, if you use a scanner, any scanner you use, there will be dots, which are called noises. Even because many persons are using, dust will come from their hands also, or normally. Now, how to remove the dust? I mean, the small points, without affecting the continuous lines which forms your thumbprint. So first you do an erosion. What erosion will do, it will take out the small parts, as you can see here. That erosion has removed all the small particles here, or the which is of the size single pixel, it has removed all. This is the effect of erosion. But what has happened? In the process, the continuous line, though it has become thin, but in many places the breaks have occurred, which we do not want, because our thumbprint analyzer will require them as a continuous line. Of course, we can use image processing techniques like filling the gaps by, like contour following kind of algorithm we can use. But here the simple algorithm is, after erosion, you dilate it again. So what will happen? The erosion, it has removed the unconnected components and some connected components also. But when you do the dilation, if there is a pixel gap, 1 pixel gap between two objects, it will again fill it, as you can see here. When you have done the dilation, so erosion and followed by dilation is known as closing. So you see the thickness has come back here, and black and white noises have been removed. So now you can, what you can do, you can combine different processes like erosion, or you do a closing, then you do opening, you use different structuring element and go on seeing it. See how the image has been reconstructed by multiple operations of erosion and dilation, or you can call opening and closing. Actually, if you open a book of mathematical morphology, because there will be a lot of mathematical rigor. And the first good book, which came in 1982 by Jacera from the School of Mines, Paris, was the first research scholar of Jibanananda to work to develop the mathematical morphology. So it talks about a lot of spaces, mathematical spaces, which is quite, you should be very knowledgeable about mathematics to understand the maths. But the first algorithm, or the first theory it presents, is called a hit or miss algorithm. They don't talk about the erosion and dilation. since we work on images, our job is to work. So it is easier to first say about erosion and dilation because we'll be using those as operations. But the important algorithm, there is only one theory there are, just one theory, which is known as heat or miss. The heat or miss, from heat or miss, you can generate actually your erosion, dilation, opening, closing, everything. Just one theorem, that is called heat or miss. So what is heat or miss? So if you have an image, as we have seen, that it is X. X is your image, object points. And you have got structuring elements. So let us consider there are two structuring elements. One is called A and one is called B. Now heat or miss means that you consider those points only where, first of all, let me tell you the heat or miss A and B, as I say, two structuring elements, they should be totally disjoint. And by heat means the A should hit. That means that A should hit the image foreground and B should miss it. That means what? That means B should hit the background. So A is hitting the foreground, B is hitting the background, which is known as hit or miss. You see, some simple application. Suppose we want to find out the location of D. As you can see, there is a boundary is there, small background. This is W. Now, what is the complement? As you can see, A means our image object points, that is C in an D in an E, as you can see. And what is the complement of AC? The set of all shapes, that is CUDE. So if we erode, this is called the complement here, because we do not have these things. Now if we erode A by D, what you get? You will get a single point. This one, it will get removed. This will be there. And if you erode AC by W1, I mean with this, then what you get? You get this one. Now if you take the intersection of both, then you will get the location of D. I mean, this is very useful when we want to find out the corner detection. If I have any image of corner, I'll show you. I do not have that. Now, you remember I told that erosion is an important operation on the boundary. It removes the boundary pixels. So if it is removing the boundary pixels, that means there must be a way to locate the boundary. In image processing, one of the important problem applications is to find out the boundary pixels. How to find out the boundary pixels, which is also known as edge detection. So how do we do the boundary pixel detection using morphology? Since erosion removes your boundary pixels, so if we take a set difference from the original image and the boundary pixels, what you get? You get only the, original image minus the eroded image, you get the boundary pixels. Am I clear in this?
Yes, sir.
Okay. This is a very good one. We have used a 3x3 structuring element. And if you take original, these are very good images we're showing, but actually when we do the practical images, then you have to do noise cleaning, filling the gaps, everything, then you get such kind of image. And then you can find out the boundary. There is another important, as I told you, that region filling. In many cases, you will find that there are some places it is not filled. See the algorithm here. We take an initial point here, object. Then on the background, we do the dilation and intersection with the background. This is known as conditional dilation when it stops at the boundary. So go on repeating the step till you get idempotence, means there is no change. So you generate shape. This is the application of region filling, because when you have done, you've got small holes inside. How to fill the holes here? Because many times when you take the image and then we do the threshold, these are the problem we get, where we get actually in the industrial inspection system, where in the conveyor belt, a lot of objects are moving. Then to identify the objects and accordingly separate them out is one of the kind of impression application. So this is how to fill the holes. Small holes, we have done the filling. This is called connectivity application. These you can see. What are the connected components? To find out the different connected components here. So you've got an image, this is an X-ray image. We want to find the bones here. So this is the connected component. Finding out the connected components. What it is doing? It is dilating and intersecting with the. You take a point, go on dilate, and then intersect with this image. Then you get this kind of image. Shall we take a break of 5 minutes? Or if there is any questions till now?
So for there's one.
We'll break for 5 minutes, ask for questions from the audience because the topic will change now.
Understand? Now the participants are requested to post your queries in the live chat box, and your queries shall be answered by Dr. J. Rai sir.
Sir, good afternoon, sir. So here's one question from Nanda Kishore, sir.
Yes, I can
Hello.
hear.
Yes.
I can hear.
Sir, please provide MATLAB programming for these operations.
I mean, I cannot provide the programming, but in MATLAB there are libraries in the MATLAB for mathematical morphology. You can directly use it. And let me tell you how you can use it. You can write a simple algorithm. Suppose you have got a 3 by 3 pixel. Let me share again the screen. Now, these are don't care locations. This is the center, and we have got suppose this kind of structuring element. Now, writing a program is very easy. Suppose you like a convolution you put on this image and do the AND operation or OR operation. What is AND operation? AND operation will give you the erosion, and if you do OR operation, it will give you the dilation. Equivalently, the whole image you can translate. Translate means what? From the origin, if it is there is 1 in the horizontal direction, then you translate on the horizontal direction and take the OR operation. If you take the OR operation at each point, you will get your dilation. If you take the AND, it will give you the erosion. It is very simple to implement. Whether you do it like a serially process it, or in your mind you think it is a parallel computer. So whole image you shift along the points of the structuring element and take AND operation or OR operation. See, in MATLAB it is very simple to do, or in MATLAB nowadays you have got the library also. Thank you.
That's also. Yes. Please, the participants have any questions? Drop in the live chat box.
What is a researcher school? Researcher school. Hello, sir.
Yeah.
So we have one question from Harmona Ram. Sir, what is the research scope in image registration?
Image registration.
Yes, sir.
In the image registration, what is image registration? Image registration means you have got a reference image and you have got your test image. The test image what you have got, that you have to register with the reference image. This is your registration problem. Now, how it is done? It is done by locating points which are common to both, and it is equally distributed over the image, and then fit a mathematical model. Usually from satellite image, when you take a satellite image, it will have the distortion due to the Earth's curvature and the imaging process. Then you have to register with a map. And for that, you require what is easier to detect is a road crossing or a river crossing or a particular boundary corner, a building corner, like that. Now, through morphology, what you can do that on the threshold images, you can locate the points. You can choose the points which are very easily, because it is always a problem in a registration to locate the points. Which points should be taken? It should be equally distributed and which should be easily detectable both in the reference image as well as on the test image. So morphology can be used to locate the points, registration points. Thank you.
So we have another question, sir, from Mr. Abdul Malik. What is graphic card and how to it relate the image processing?
What is graphic card?
Yes, sir.
But the graphic cards, there are different kind of graphic cards. The usual graphic cards, what we see now in the laptop, it comes there. But there are many dedicated cards. In the cards you can have, there are dedicated cards which does your dedicated image processing problems. There's the only thing. Or there are video cards which extract the image and audio so that there is no disturbance. So in image processing, you can use video cards in two ways. One is the video card, you can have the dedicated operations already inbuilt in the hardware, one thing. And nowadays people use the video cards, because video cards have got higher processing power. So we use the GPU power for carrying out operations. And since image processing is a time intensive, CPU intensive job, so the graphic card CPU, which is called the GPU, graphic processor unit, is also used. That's how we can use it in the image processing.
So we have another question from Nanda Kishore, sir. Any suggestions on research based on morphological image processing?
Yeah, I mean, in morphological, see, now morphological imaging can be used almost everywhere. And initially it started with binary images. So most of the applications have gone. And initially it was on geological or mineralogy. So more work was done on that side. Currently, the morphology was developed later for gray label images. I have spoken in the gray label images, what you do, instead of taking as and or, as we have done for binary images, in gray label images, we use the max and mean operations. What is mean? Mean means it is intersection or and operation. That means in a gray label image, in the neighborhood, you find out what is the minimum. That is called erosion. And when you take dilation, you take the maximum. That is called gray label image. Now here, the research topic, since it's developed on black and white images and gray label images, it was extended for colored images too. But in colored images, we know the color fundamentals. I mean, the way color affects our eye, because it has got three different images called red, green, blue, and different kind of mixture of red, green, blue. Red, green, blue will give you a color. So we know how they're intermixed. But in the research topic now, nowadays satellites will be having hyperspectral images. That means there are multiple images. So it is no longer two dimension. There is a third dimension too. That means you've got a set of images of the same area. And it is not exactly RGB, red, green, blue, but it has got some spectral dependency. So a research you can do on the satellite images, hyperspectral satellite images. That is the open topic now. And many people are working on that. Thank you.
Sir, we have one more question, sir, from Anup Bhatt. How encrypted cared card image is being extracted?
How? Can I see it
Encrypted,
here? I can see it here.
encrypted cared card image is being extracted. This question is from Anup Bhatt.
I'm not getting the question
Sir,
actually.
we can watch in YouTube, sir.
But in YouTube,
Chat box to post. Push it.
So we'll just paste in chat box now, sir, the question.
please.
I will read out the question. He says how to cared card, C-A-R-E-D, cared card. How encrypted cared, C-A-R-E-D, cared card image is being extracted. It's not clear.
It's not clear, and I do not know. I do not know about the cared card. Thank you. I can't answer this question.
Sir, we have another question, sir, from Mr. Anuja. Which is the best image segmentation technique can be applied in FPGA?
FPGA.
Field Programmable Data Link.
Okay. See, the first of all, you should understand when we talk about digital image processing, there's nothing which is best. There's nothing which is best. So depending on the kind of problem, you have and the kind of resource you have to choose the algorithms, or you have to test multiple algorithms and you choose the best. Now, when you're talking about FPGA, definitely you should take the advantage of the FPGA. That means the algorithms which can be implemented parallelly or in hardware operations, those should be used. Those kind of techniques should be used. And morphological technique is very good for implementation in the hardware. So for segmentation, you can use even morphological techniques. Thank you.
Sir, one more question, sir. Can you please explain geodesic morphology in relation to image processing?
Yes. Now, let me talk about the Euclidean space or Euclidean distance. What is Euclidean distance? We know. The Euclidean distance between 2 points is a straight line, like on the space. Let me share screen. What is the Euclidean distance from here to here? 2 points, if you take the formula in a two-dimensional case, the formula is what? It is, suppose 2 points are there, x1, y1 and x2, y2. What is the distance? It is the square root of x1 minus x2 square plus y1 minus y2 square. Or simply, if you draw a straight line, the length of the straight line. That is in the Euclidean domain. But actually, the morphology was implemented using the concept of geodesy. Geodesy, as it says, I mean, the term is related to the earth. Like on the earth, if you want to find out in a map, we do not consider when we calculate a distance on a map, we put 2 points and just with a scale we measure it, what is the length. That means it's a linear scale. But do you think that is a length, or is it the shortest path between 2 points? When you consider India and US, if you find out the distance, then you will see that it is over the earth. So there is a curve involved in that. So there are many curves through which you can connect point A to a point in India to a point in United States. because there is no straight line which can connect these 2 points. You cannot go under the earth, on the top of the earth. So this is called geodesy when you consider that the geographical feature of the earth. Now the same processing has come, same concept has come even in 2D now. Geodesic distance of a curve, of a object, of a binary object, you can say, or it's an object when you take an image. If the object is convex, convex means a circle is a convex, a triangle is a convex, but something like a horseshoe is not convex. What is convex? That means for every point to every point you connect it, then the whole line should be within the object. So that is called convex. If you go to a non-convex set, your shortest path is not a straight line.
Sir, one more question is this, sir.
No,
I think we are running short of time for
okay.
next.
Okay.
Okay, sir. At the end of the session, I will read out, sir.
Okay, thank you. Shall we take a break for 5 minutes?
Okay.
Okay, sir.
So the live stream is going.
I want break. I want break. In the break time, post the questions.
So all the participants are requested. Please post queries which will be answered by the Dr. J. Rai sir at the end of this session. Take a 5 minutes break and join.
Hello,
Sir,
Professor
okay,
Kuliappa.
okay, sir, shall we proceed, sir?
Yeah. Can you see it?
Yes, sir. Slides are visible, sir.
Shall I start?
Sure, okay, sir, proceed, sir.
Now, some of the questions in the previous lectures, people ask questions which are actually related to satellite remote sensing. Now, remote sensing is a field of image processing, you can say, where the imaging process is completely different than the images we acquire in our normal cases, like with a camera or a application to a inspection system, or tracking of your images, tracking of objects, all those things. They use a normal camera, which is basically a black and white camera or a color camera. In a color camera, you've got 3 colors like RGB. But when we go for satellite, we have got the imaging process is totally different. So we require, and we have got different kind of problems in remote sensing images satellitely acquired. Now, what is the plus point of image in remote sensing is because it gives a very wide view of the Earth we are seeing from the top, which is known as the synoptic view. And you can, because there are many satellites and they are orbiting the Earth, the same place of the Earth, you can take a different time at different dates. So when you do, the most of the application of remote sensing is there for agriculture is one of the very important part. And another thing is the military, that is also another important part. So wherever you take, whether you take cultivation or a military movement, one of the important part is in the cultivation, your problem could be to find out the kind of pest infection if you have, the stress factors of the plants, like whether some plants are growing properly or some plants are not growing properly, and how much area you have got the agriculture, so then you can calculate, you can predict the yield, which will be useful for the planners to plan that how much of agriculture they will get this year, so how much you have to import, how much you have to export, and all those things. And in military, you can this is used to find out the troop movements or vehicle movements at different places, whether with a camouflage or without camouflage, open, how many tents are there, and all those things. You must have heard the recent military, I mean, in the last 1 or 2 years, that how remote sensing satellite images they've used. So in remote sensing, the plus point that the way the imaging is taken, the imaging process itself is different. That means when we take with a normal color camera, actually what we're doing, we are taking the images as if whatever we see on the naked eye. I mean, what you see is what you record in an image. That is our normal color camera. But when you use satellite images, it takes images at multiple spectral bands. It could be infrared band, it could be thermal infrared band, it could be the middle infrared, it could be shortwave band, because the electromagnetic spectrum is huge. And out of that, only in a narrow window we can see, which is about 400 nanometer to 700 nanometer, we can see. That is called the visible band of the electromagnetic spectrum, which is visible to our naked eye. But there are so many other bands which we may not be seeing it. Some animal might be seeing it, but it will be easier. Suppose nighttime some people are moving, how to see the person is, if some movement is there? Or nowadays during this COVID case, how to know without touching a person when the person is having fever? You have seen that they use a camera, which is a kind of camera. It's a camera only, but it has got only one sensor. It takes near your forehead, it takes the temperature. That means that is also imaging, but what kind of imaging? It is taking the reflected IR, or the thermal IR, infrared. That there. If you have high temperature, you get a higher value there. A camera, there are cameras, bigger cameras, which are used in the airports, where you can screen when a lot of people are coming, whether heat, anybody is having a higher temperature than the rest of the crowd by using the camera, so which is not visible with the naked eye. That is the kind of thing what you get in satellite imaging. That's why it is important. Nowadays, there's a rampant use of drones. The drone you can use everywhere, because drone has got the visibility, less visibility, but it will have a better resolution. And satellite images here, repeatability, that means to revisit of the same place, it may take few days or a week, or maybe the next day, but it takes a lot of time to process. And the drones, the problem with drones is it is at a lower, it runs at a lower altitude, and the camera, the kind of camera satellite is having, they cannot use it because they will be very heavy to load, and it's not suitable for a very big area when you want to find out agriculture over a big area. Drone is for a short time kind of thing. Also, drone will have the problem in the, if there is, it is raining and all, if there is a storm, the drone will affect, but in satellite, it is quite high. But also the problem is the satellite-based sensors, since satellites, remote sensing satellites are placed at an orbit of nearly 700 kilometers. So it is above the cloud. And if there is a lot of cloud, you cannot see the Earth, except your microwave radar imaging, which is again, it can take images. But with a drone, you can take even below the, even if cloud is there, you can take. Drone also requires permission from the local authority, like in the bordered area, you cannot run a drone. Now, what are the different sensors which are used in satellite imaging? It is we take the satellite images, records images in the visual range, but the visual range is again divided into three parts, like red, green, blue, and we take the near infrared and mid infrared. And nowadays, because we have got the advancement of camera technology, and the satellites are able to carry higher loads. So we have got even imaging at a narrow bands, like the sub bands. The infrared will be divided into many sub bands. So these are known as hyperspectral imaging. Now, why we take in different bands and why we use, what are the use? Like we know, as you have seen that in our signaling system, road signaling or train signaling system, we use three colors, red, amber, green. It has got some property to our eye, so that because of that we take it. But when we record images of the Earth by the satellite. Satellite remote sensing means the imaging of the Earth. Why we divide into different spectral bands? So because of the property of the land use features of the Earth, like the green vegetation absorbs the energy in red and blue band, but reflects in the green band. That's why we see the vegetation as green. So if you take images red, green, blue, in green you will find higher value, and red and blue you'll get less value. That's why the green leaves look green. But in infrared, the green leaves reflects energy, but moisture content in leaves absorbs a few narrow bands in the infrared range. Why? What? But why not only green band? Why we need the infrared band? Because infrared band also tells you, other than the chlorophyll content, like the green color, it also tells you about the moisture. So if you have a tree that is green, and if you have a model of a tree painted as green, if you take the image with a normal camera, what it would look like? Like in the movies, the props are used, all are made of woods or maybe plastics nowadays, but it looks like real because we are seeing it with our naked eye. But how to differentiate that whether they are really tree or they are not, or whether after a storm the trees fall or trees die? How to know which tree is dead and which tree is living? Both will show green color. So then we use infrared, because infrared gives you the moisture content in the leaves and the chlorophyll content also. What is the use? Like the old days, if you see that the army movement in a hilly region, they used to move with small tree trunks, tree branches, and behind the branches they will hide, and slowly they'll walk with the trees. So you're camouflaging with the tree. Or if there's a tank movement, when the satellite images came, when your tank or vehicle movement, you paint it with green so that satellite image cannot see it. Or from the distance with a binocular, you can see that it is only green things. Or they cover it with dead leaves. So when you take images in infrared, you can clearly differentiate between the dead leaves and the live leaves. Also, a metal or plastic object which is painted green and made it look like a tree, and the actual tree can do the differentiation. That's why we take satellite images in different bands of the electromagnetic spectrum. As you can see, in the lower range, you have got X-rays, gamma rays, ultraviolet. There are some imaging in the ultraviolet, that is when you do hardware inspection and all. But we're talking about remote sensing, so it will come. See the visible range, you can see it is a narrow band only we can see. It's a huge magnetic spectrum, electromagnetic spectrum, we can see only the narrow range, which is about 400 to 700 nanometers. From 700, you start getting the infrared. Infrared is again a big band. After infrared, you get microwave. Then you get the radio waves, like the FM, AM, shortwave. Then long radio waves are the shortwave. Everything comes after that. Now, imaging you can do anywhere. If you have a sensor which can detect your waves, radio waves, or microwaves, or infrared, you can do that. Recording. Now, but mostly in satellite imaging, we use the visible and the infrared. The infrared is sometimes subdivided, which is known as hyperspectral imaging, because in a different spectral bands we are taking. So 30 years back or 40 years back, it used to be multispectral. That means you are having 3-4 different spectral bands. But now there are so many narrow bands we take images, so it is being called now as hyperspectral bands. Now you can see at different spectral band how the Earth feature behaves. Like the water, you can see blue only. In the visible range, it will reflect something. Blue is very soft one because it doesn't go much. So blue color only is in the visible range, and little bit you can see in the near infrared. But in rest of the cases, like in the infrared, mid-infrared, near infrared, it will absorb. So it will show you only blank or black. Whereas if you see the soil, because soil is also having some moisture, so from the visible to mid-infrared, you can see the response, how it responds. And the green shows you the vegetation. You see how nicely it shows that only in the infrared it has got high values. In mid-infrared there are 2 peaks, but visible it is low. So what kind of image processing we should be using to detect the vegetation? Now comes in remote sensing we use the algebraic operations on different bands. This is a very important method to delineate certain features. For example, ratioing. If you take a ratio of the near infrared and the visible, we'll get higher values for the green components. The greenness, that means the vegetation. Although there are different kind of algebraic formula which is used to highlight certain features of the Earth. Like whether you want to highlight tall trees, agriculture, water bodies, shrubs and all. So you can use different kind of band combinations, which is known as band combination. When you take images in different spectral bands, they are known as bands in image processing. One of the important use is to crop a species delineation. Why it is required? Like in India, you will find there are smaller land holdings where the crops are there. Unlike in many states, many countries where miles of miles are only same thing is being cultivated. It's not. Like United States, if you go, garlic is planted in 100 miles only garlic. But in India, you will never find any place where the garlic is planted like that. So now it is, sometimes it is required to fast to identify what kind of crop is there. So accordingly, you can take action, whether depending on the weather condition, it is raining, or you required some kind of pest repellent and all those things. So this particular curve shows you of 3 different crops. It gives different spectral signature, as you can see, like corn, tulip, and soybean. So by using such information, we can design our algorithm. In remote sensing, actually, we design our algorithm. And most of the algorithm, like for analysis, is arithmetic operation based. Though there are classification techniques, the standard classification techniques like maximum likelihood or neural network based or unsupervised clustering learning, whatever you are hearing now as artificial intelligence and machine learning, those techniques are being used for last 50, 60 years in remote sensing images, because there the The need was there. Now, anyway, machine intelligence is being used in many different applications. Now, on a healthy leaf, what happens? The near infrared is totally absorbed at the bottom part and then it is reflected. Whereas the visible range is reflected before that. So you will get a higher value for reflected and lower value for the one. Now, how to find out one of the important work is the reflectance, the moisture content. What is the moisture content? Depending on the moisture content, you can define the health of the plant. So we need to differentiate the moisture content. This particular graph shows the wavelength versus reflectivity of different moisture density. As you can see, the moisture is high between the range of infrared and middle infrared, because it starts at about 700 and 1000 is actually the near infrared. The mid infrared comes up to this much, up to less than 50, up to 1200. Then of course there is another gap. So if you can design your sensor, one from 2000 to 2500, 1500 to 2000, and then from 700 to 1500, you can find out a lot of other features. This is how the sensors are developed. As you can see, the whole process of remote sensing.
Yes, sir. Yes, sir.
Okay. So, see, there are, now let me tell you, there are, any camera system, there are two kinds of camera system. I mean, imaging when we do, it is more so because we are in satellite imaging, this should be known that when we look at images, we see the reflected light. So this is passive. Passive means what? What is being reflected, we are recording and seeing it. In a camera, normal camera system also, it is what is reflected, we are recording it. But there is something called active sensors. Like you know the bats in the nighttime, how they see, they don't see. They make a sound and the sound they receive it and they know what is the distance. So these are known as active sensors. That means you are illuminating it by some kind of mechanism. Like you can say, so most of the satellite imaging is done as passive sensors. Is whatever is being reflected, we are recording it. Even the infrared, mid-infrared, visual, all the reflected light, we are actually reflected signal, we are getting it. But there is also one kind of sensor which is known as active sensors. Active sensor means you are generating it. What are the active sensors? Our active sensors are radars. Like in a radar system, you generate a signal and you take the reflected signal and you see what is the distance, calculate accordingly, you know what is there. So similarly, there is something called microwave imaging, microwave radar. So in satellite imaging, we also use microwave radar sensors. It has got the plus point of entering, see through the cloud, that means record through the cloud. But the problem is, it will not see objects the way we see the objects. It may not be able to differentiate between two different houses, two different colors. But it can also differentiate between the moisture content. How much moisture is, because microwave will be absorbed if there is a lot of moisture is there and it is reflected, it is not there. So energy source is on illumination, that is the radiation, interaction with the target, and recording there. Now, in satellite imaging, I mean, any imaging, you are supposed to have a pre-processing kind of thing. As we have seen with a normal imaging by a camera or by a scanner, whether it is a thumbprint or a human face, you will see a lot of noises. So we need some pre-processing. Here in satellite images, you have got pre-processing is very much it is used, because unless we pre-processing, cannot use it. So what are the kind of noises you can get? Because the imaging is taking place from a height of about 700 to 800 kilometers. And so the signal had to travel 700 kilometers. Now, in between, if there is any atmospheric disturbance, so signal will get attenuated, signal will be dead, as we see now in our cell phones, that many times you may not get strong signal. So atmospheric disturbances will affect the signal. So first of all, you have to correct the atmospheric disturbances. Also, due to the existence of, particles, smaller particles, there will be a lot of scattering of the signal. So you must do some processing on that. There will be some problem related with the sensor itself, but which is known what kind of error should come. So that also should be processed. So modeling the atmospheric disturbances and processing is a big task in satellite imaging. That's why satellite images, you cannot get it, just record it and send it to you. You cannot get it. It takes a day. Nowadays, it takes a day. It used to be 7 days during our, 30 years back or 40 years back. So the first thing is pre-processing. That is one kind of pre-processing. What is the other kind of pre-processing? Which is on the image itself. That means due to the curvature of the earth, what you are seeing, the image you are seeing, actually the projection of a 3D surface. It is being projected on the 3D surface. So you will have a lot of geometrical distortions here and there. Specifically when there are hills or hilly areas and the plains. In a hilly area, you will find the distance between 2 points are not same if you take from different directions the images. So you must do the correction, the distortion due to the Earth's curvature. Now, since you know the location of the satellite, the angle and the Earth curvature, you can model your this technique to rectify these errors. What are the other kind of errors you can get is due to the sensor. That is an error which can be done. And finally, as someone was asking, one of the important tasks is to, when you take the image, you can say it is Delhi or it is Hyderabad. But how to know where? Hyderabad, which point? Now there is Google Earth, which has come out in 2000 or 2005. In Google Earth, from Google Earth, you can see the location. Your car, you can navigate. You can find out the location, the latitude, longitude. But when you take a satellite images, do you have the latitude, longitude recorded in that? You do not have. So that means you have to register the image with the map, which is having the Earth coordinate system. It could be latitude, longitude, it could be the meters, whichever way it is. You must register the image. So with a known map, some registration is done automatically because we know where the images have been taken, and there are some standard points, standard registration points on the Earth, on the map, we know. And on the images, we automatically locate those points. We know we are going over Hyderabad. So Hyderabad, this particular point is there. So we automatically we find out and do some automatic registration, a crude registration. It is given to the user, and if you need it for a better one, you do it yourself with the aid of a map. Another kind of imaging is done with satellite is called stereo imaging. Because image, when we take through the satellite image, you get only one image, which is the projection of the Earth. You have no idea what is the height. But to know the height, as we do is a stereoscopic imaging with our eye we see. That means both eyes see the same object from it by a distance between the two eyes and the depth. And through that, you can get the perception of depth. Similarly, in satellite images, we take stereo images. How they're taken, either they will have two cameras, or the satellite on the next day when it is visiting the nearby areas, it will tilt the camera and take the image. But that is another kind of processing you require, because in stereo images, to properly find out your depth, you need both cameras to be parallel, which is impossible if we take on the next day. So that is the kind of processing we require. How to make both images as if you are looking with two cameras having their axis parallel. See the kind of reflectance you get. There's not much of difference in the visible range, but in the near infrared, you see, if the healthy leaf will have very high value, when the sick leaf will have little high, but dead leaf it is nothing. So you can accordingly calculate. Now, imaging actually, since we give me some more time, since we do the analysis of satellite images and we take the images, we must know how the imaging take place. I mean, what are the characteristics that is used for the imaging? The Earth is rotating on the east-west. I mean, the axis of rotation is in north-south. Now, satellite image, if it has to take the whole of the Earth, yes, it has to move in both directions, which is not possible. So it takes care. I mean, satellite image will move on a north-south direction, so off polar orbit, and take advantage of the Earth rotation in the east-west direction. So automatically Earth is moving and satellite is taking the photograph. So that's why it is put at 700 kilometers away. Of course, there are other satellites which are communication satellites, which also takes the weather satellites that are much higher altitude. Sometimes it is in the geosynchronous orbits. The geosynchronous orbits are at 36,000 kilometers from the Earth. So the resolution of images is poor, but we get a wide area and we can see the cloud storm movements. So they are known for weather applications. But remote sensing satellites are at a much lower altitude. Even spy satellites, military satellites, they go at much lower altitude, but they do not survive many days, maybe a month or so, because Earth will pull it inside. Another thing is when we take the images, suppose we take one image, you will be taking many images. Next area, Now to compare, sometime you may require to mosaic both the images, add both the images. So both the images should have similar illumination. So usually satellites, when they take imaging, it moves in such a way that it takes the advantage of Earth's rotation so that it doesn't have to move on the horizontal side, like east-west, it doesn't have to move. It automatically it records. But how to get the same illumination condition? So it is put at 700 kilometers so that, and in such a orbit that your time of imaging is same as the local area. Usually it is 10:30. At 10:30 you are taking in India, at 10:30 you are taking at Delhi or Bangladesh, Nepal or anywhere, it is 10:30. So your images are having a equal illumination. I'll show you some images. Like the old days, the low resolution images. So images were being used only for agriculture. That was the Landsat images, multispectral images at 80-meter resolution. Later on, the same Landsat thematic mapper had 30-meter resolution. Even the Indian satellites, when we started sending satellites, it was 22 meters resolution. And now, and the French satellites which came around late 80s, it had 10-meter and 20-meter resolution. But nowadays we have got sub-meter resolution, like 0.2 meters, 0.6 meters and all. So we can detect even a car movement, it can detect. Just to tell you the terminology, panchromatic means when you have got a single band image, it is a black and white image. In multispectral, there are 4 bands or 5 bands. That means other than the red, green, blue band, you have got the infrared band and maybe sometimes a thermal infrared band. But in hyperspectral, you have got multiple bands. See the effect here? The single band quality is much better if you see the visually, if you are doing something. For visual processing, like drawing of roads, road network or water body network or something like that, it is always better to use the panchromatic image. One of the another algorithm we use in satellite imaging is when we merge a panchromatic image with the multispectral image, so that you get the color. You are actually putting the color on the panchromatic image. So you got the sharpness here as well as color. How it is done? It is done by doing the hue saturation intensity transformation. You do the hue saturation intensity of the RGB image and replace the intensity with the panchromatic image. When you see the image, it will give you a color. What makes satellite imaging so important is it is known as temporal resolution. Temporal resolution means the same area you can analyze over time. So you can know if a new feature has come or not, or if there is any change in the crop pattern, whether there are locusts have eaten away your crop, all those things you can do with that. With the satellite images, from satellite images, finally what we do, we also create maps, the initial maps, and we do the ground truthing, means we go to the field and then accordingly we update our map. All these, whatever you see, the Google map and all, they have done in this way. From the satellite images, initially you have drawn the map, and then you go and correct it by visiting some selected locations. So some satellite imaging also gives rise to another subject, which is based on computational geometry and database, known as geographical information system. So the maps that are created are put in a GIS along with the data, attribute data, and the analysis is performed. I think I'll stop here and take the questions now.
Thank you, sir, for your valuable lecture. And we came to know the use of high-level mathematics in morphological operations and applications in image processing and CV applications in remotely sensed images, sir. Thank you, sir. Now the participants are requested to post your queries in the live chat box in the YouTube, and your queries shall be answered by JB Raisa.
So, hello, sir.
Yeah,
So here is the
Vivek.
first question, sir, from Deepthi Karani. What should be configuration for 3D images?
Configuration for processing of 3D images.
Yes, sir.
I mean, 3D images, if you see, there are two ways. When we do 3D images, that means we have stereo images. So to process the stereo images. So there are some hardware system, they are known as photogrammetry systems, digital photogrammetry, which processes the stereo images.
So here is another question from Varaprasad. What are the best restoration algorithms for hyperspectral images?
Restoration algorithm. But see, whether it is hyperspectral means you've got same image, multiple images here of the same location. Otherwise, it is image. Now, when you go for restoration, I believe that in some bands you are not getting good signal. So what we do, we take the nearby bands, or if we know which feature is disturbed, we select one of the such band in the hyperspectral domain, and we replace or fit a mathematical model to extrapolate those locations where there is a defect. Thank you.
So we have another question, sir, from Abdul Malik. Which is the best software which relate to digital image processing?
There is nothing called base software, but the popular softwares are PCI Geomatics, or which is known as Geomatica. This is one. Then we have got from ER-8-, which is known as Imagine, IMAGINE. These are the two systems which are very popular. Thank you.
So another question from Selvaraj Das. Is tensor analysis useful for morphology?
To understand, if you do the, just a minute, please repeat the question.
Is tensor analysis useful for morphology?
Tensor means it is D.
No, sir, he didn't ask like that. Is tensor analysis useful for morphology? Question mark. Tensor, T-E-N-S-O-R.
No, I have no idea. I do not know this.
Sir, one more question, sir. Can you please give the list of sites to get satellite image for data processing?
That means free satellite image.
They just ask for satellite image, sir.
You can go to, you can search for Sentinel. I'll write down here. Sentinel.
Sir, last.
Good afternoon to everyone present here. I hope you all had very informative session on behalf of the Department of Electronics and Communication Engineering, Gates Institute of Technology, and the participants. I, K.C. Kulayappa, HOD of ECE, great honor and privilege to thank the speaker, Dr. J.A. Rai sir, for all the valuable information and research ideas he shared with us this present time. Thank you, sir. Thank you so much.
Just a minute, I have shared the satellite data site here in the chat.
Chat box, sure, sir. We'll post it, sir.
Okay, thank you, everybody.
And thank you, sir. And I thank all the participants who have given their valuable time to attend the session. Thank you, everyone. Thank you, sir.
Okay.
Thank you. We will
Bye-bye.
end the session. Thank you, sir.
Okay, bye. Good day.